Hello everybody and welcome back to another visual pattern challenge. Here's our visual pattern today, and boy, this is a super tough one. Here's step 1, here's step 2, step 3, they've even given us step 4, and your challenge would be to predict the number of these, well, these are little spiky balls. I'm going to call them coronaviruses, the number of coronaviruses in step 5. If you can do that, good for you. Can you then set yourself the challenge of predicting the number in step 43? It's going to be a huge number. And can you write an equation that could be used to predict the number of viruses in any step at all? So that's the challenge. If you'd like to accept it, pause the video and see if you can work it out. Okay, so this pattern looks like it's growing pretty rapidly. I guess let's just try to get some visual intuition to predict step 5 here. I'm seeing 3 viruses to start off with, and it looks like those are right there, and it just kind of makes a mirror image. So that doubles there. And then here, it's the same thing, right? Here's step 2, and then we've just doubled it over to the right. So first we doubled it down, and then we doubled it over to the right. And then we're doubling it down again. So what I would expect is for step 5, we'd have all of this in step 4, plus this sort of shape doubled here. And let's see, there are 6 in each of these little arms, so that's 24 plus 24 more. So step 5 should be 48 viruses. That's my prediction. Well, let's take a minute to analyze the numbers here and see what kind of a pattern we have. I'm sure you can tell it's not going to be a linear pattern. It's going to be something different. But let's make a chart with the step number and the number of viruses. So in step 1, we've got 3. In step 2, that doubles to 6. In step 3, that doubles to 12. In step 4, 24. And in step 5, we're predicting 48. So when we approach patterns like this and try to analyze the numbers, we usually take the differences. And if it's a quadratic, we want to take the difference of the differences to confirm that. Something interesting is going to happen here. Let me show you. So 6 minus 3 is 3. 12 minus 6 is 6. 24 minus 12 is 12. And 48 minus 24 is 24. So I got 3, 6, 12, 24. And what I started with was 3, 6, 12, 24. And I can do this again. 6 minus 3 is 3. 12 minus 6 is 6. 24 minus 12 is 12. 3, 6, 12. So you could do this forever, go on to infinity, taking the difference of the differences, etc. And you'd get this same pattern repeating. This is something we see with exponential functions. So there's some number that's the base, and then the variable, the x, is going to be the exponent. But what is that? We've got some number that we don't know yet, and some exponent, and maybe other stuff going on, maybe some multiplication, or I don't know, could be other stuff. But this would be the core of it, some number to the x power. Is it 3? That's the first question. So I see 3, 6, 12. These are all multiples of 3. Is it 3 to that power? Well, that is going to lead you down a wrong trail. What you want to look at is not, what the multiples of these numbers are, but how much it's increasing. Is it doubling? Is it tripling? Is it quadrupling? That's where the base for your exponent is going to come in. And when something doubles, that means it's 2 to some power. So for example, 2 to the 1 is 2. 2 to the second is 4. 2 to the third is 8. And you can see those are doubling every step. So we want 2 to some power. And then to get the number here, like the 3, 6, these are all multiples of 3, we're going to multiply by that. So this is the formula we should start with. It's not perfect yet. If we said y equals 3 times 2 to the, let's say the first power here in step 1, so we're going to put 1 in for x. Well, 2 to the first power is 2 times 3 is 6, but we only have 3 here. So that doesn't work. What we actually want to do is subtract 1 so that this first step is to the 0 power. So now if I put in 3 times 2 to the 1 minus 1, I put in step 1 for x, I'm going to subtract 1. That's 2 to the 0 power, which is 1 times 3 is 3. If we try that in step 2, that would be 3 times 2 to the 2 minus 1 power. That'd be 2 to the first power. That's 2 times 3 is 6, and that's how many we have there. And try one more, 3 times 2 to the 3 minus 1 for step 3. 3 minus 1 is 2, 2 squared is 4, times 3 is 12. Yeah, that's how many we have. So we actually have to adjust the exponent by subtracting 1 from our step number there. So this equation, you can test it with steps 4 and 5 if you like, but it is going to work. It's y equals 3 times 2 to the x minus 1 power. Once we've done that, all that's left is to figure out step 43, and we can do that by just plugging 43 in for x in our formula. So y equals 3 times 2 to the 43 minus 1 power. So that's 3 times 2 to the 42nd power. And I'm using my calculator for that. I'm going to punch in a 2, hit the x to the y button, punch in 42. I'm getting a really big number. I'm going to multiply that by 3 and get an even bigger number. And the one I get is, let's see, 13, 194, 139, 533, 312. And let's see, this is thousands, well, hundreds, thousands, millions, billions, trillions. This is 13 trillion, 194 billion, 139,533,312 viruses in step 43. Well, how did that go for you? Were you able to see that it was doubling in this kind of mirrored way? Were you able to predict step 5 correctly? If you did, great, that's fantastic. And if you went beyond that, I would love to hear about it. You should definitely pat yourself on the back if you got an exponential equation like this. Well, let me know. Thanks, everybody.